Okay, this is a video for Tuesday, September 1st. So I wouldn't recommend watching 2 videos in one day. If you want to, you can. But this is really the video for Tuesday. Hopefully it'll go by pretty quick. Essential question, how can I graph relations and identify functions? So we're still talking about functions, how to identify them. What I want to start off with is determining how we can see if a function is really a function or if it's just a relation. We had kind of discussed this in class already, but I really want to make sure that we understand it. To have a function, you could have something where you have a scenario, and I'll just kind of draw a table, where these are my x values, these are my y values, and actually I'm not going to write y, I'm going to write f of x because that's the direction that we're going. So x, let's say we've got -3, 0, 4, and then I've got -2, 1, 7. So I've got these inputs and outputs. An example of a function would be something of this nature where you've got an input that produces exactly one output. So something like if you put in -3, you're going to get a -2. If you put in a 0, you could potentially get a 7. So it doesn't necessarily have to go straight across. You'll see tables like this in the future. They're just telling you what input would give you which output, right? You could have a 4 giving you a +1. So it's okay that these cross like that because really for every one input you have exactly one output. And we kind of talked about this already in class. I want to make a note that each element in the domain corresponds with exactly one element in the range and that makes this a function. So it's really important that we understand for every one input, we should only get one output. Regardless of what the output is, we should have one output for every one input that we put in to our function. So now if I'm talking about something, an example where there is something that is not a function, I would have something like this, where I've got a similar table with my x values and my f of x. And I'm going to draw a table with a couple values here. So let's say I've got 2, 3, 4, 6. And these are just examples, random numbers that I decided to pick. -3, -1, 3, 6. So it would be possible, if this was a function, it'd be possible for me to have 2 equals -3, right? 3 equals -1. Say they went straight across. 4 equals 3, 6 equals 6. But the second I get into something where 2 equals -3, but it also equals +3, this is what makes this not a function. So there's one input that has 2 different outputs. This is not possible. So I'm going to make a note that this is not a function because, notice I'm abbreviating. I want you guys to abbreviate whenever you can. Not a function because one input has 2 outputs. So I want to go back up. If I look at my previous example, I do want to go back and reference it and say, it is possible for -3 to give me -2 as an output, and then 0 to also give me -2 as an output. This is okay because notice this, oh, you know what? Let me rewind that. If that's the case, I need to get rid of this stuff. So it would be okay for me to have this scenario because really this input has one output. This input has one output. This input has one output. So regardless of what those outputs are, even though 3 already had an output of 2, -2, it's okay for 0 to also have an output of -2. That is quite all right. So I want us to get comfortable with that, be okay with that. It's okay for two different outputs to have two different inputs to have the same output. However, it is not okay for us to have one single input that has two different outputs. So I want to really emphasize this. Hopefully this makes sense. If it doesn't, ask me in class and I will gladly clear that up for you. I had kind of mentioned the vertical line test in class, so this is the definition of that. So the vertical line test just says that if there is a vertical line that passes through more than one point on the graph of a relation, then the relation is no longer considered a function. It is not a function if you have, and this goes back to what we just said with the table, except I gave you a table representation instead of a graphical representation. So if I were to look at a graph to kind of give you guys an idea, let's say that I had a graph that looked like this. This would not be a function because of the fact that if I were to draw a vertical line anywhere through this, I would have two different outputs for this one input, right? So there's one input. We said the inputs are my x values. So if this is my input, technically I have one output here and I have one output here. So that means that this is not a function. It's important that we know this and that we can identify this, whether it be on a graph or on a table. In the future, we're going to be able to identify this using equations as well. But for now, I just want to focus on graphs, tables, make sure that we understand this concept. You cannot have more than one output for every input that you have. If we go on to the next set of slides, two more definitions that I would like for you to know. There are two sets of variables or two sets of things that we'll refer to going forward in the future. Independent is any of my x values, and the dependent variables are all of my y or my f of x. So really, the function, whatever comes out, the output always depends on whatever I put into my function. So my output is dependent. It depends on those x values. So based on whatever I put in for x, that will change the outcome of f of x. So important that we know why one of them is dependent and one of them is independent. Sorry, I didn't mean to highlight that. So important that we know those two definitions. One last slide that I want us to go over is writing and evaluating a function. So we're going to start using function notation. I typically will not ask to see y equals anything anymore. We're going to start writing it as f of x equals some kind of rule, right? So if we look at this, tickets to a concert are available online for $35 each, plus a handling fee of $2.50. The total cost is a function of the number of tickets bought. What function rule models the cost of the concert tickets? Evaluate the function for 4 tickets. So not only are we writing a function, but we're also going to evaluate the function for 4 tickets specifically. So if I look at this, I want to relate what I know here to the math terminology that we've discussed, right? So this is my relate section. I'm going to relate. I know that my total cost is mentioned here. And that is dependent on the cost per ticket. So my total cost depends on my cost per ticket. So I can start to write my rule based on this. So total cost is cost per ticket times the number of tickets that are actually bought, right? Number of tickets purchased plus this $2.50 handling fee plus handling fee. And I hope that didn't get cut off on the video. I apologize if it did, but that last thing that I wrote is the handling fee. So once we've got it written out in words, I can go ahead and define certain values. So let me move this up so we've got just a little bit more room. So if I define things, I'm going to say that let's let T equal the number of tickets bought. Then I'm going to say, well, I know that cost is what depends on the tickets, right? So I know cost is my f of x, really, or it's my y value. So I'm going to represent it. We don't always have to say f of x. I'm going to say c for cost, and it depends on this variable t. So the cost depends on the number of tickets. And we can label that as our total cost. So now I'm at the point where I have enough information where I can actually write my function out. So I know I'm going to start with the c of t, just like I typically would start with an f of x. So c of t is going to equal, and I said, okay, so total cost, which is this right here, is my indicator for this equal sign here, which doesn't look like an equal sign, so let me fix that really quick. So total cost is cost per ticket, which we can look back up here and we know the cost per ticket is $35 each. So I've got $35 times the number of tickets sold, or purchased, sorry. So the number of tickets purchased, we had said, is going to be T. So 35 times T plus, so I'm going to put my little plus sign here, whatever the handling fee was. So if I look back over here, handling fee was $2.50, so 2.50. So there is my function. I've written it out. Now the final thing says that I need to evaluate my function for 4. So 4 tickets specifically. So I can use this same function, and I'm going to go ahead and evaluate. So I can say C of 4, because it's 4 tickets, is equal to 35 times 4 plus 2.5. I can leave it at 2.5 because I know ultimately that I'm talking about dollars, so I can convert it back in just a minute. So looking at this function, all I have to do is 35 times 4 is going to give me 140. So I know C of 4 is equal to 140 plus that 2, I guess we can leave it as 250. Sorry, I don't know what I'm thinking. So $140 plus the $2.50. So the cost of 4 tickets is really going to equal $142.50, right? Easy enough. So we have to analyze the function, determine what information is given to us, what is my dependent variable and my independent variable, and then I can write out a function from there. After I've written out a function, it's easy enough to just substitute a value in and then solve for whatever it is that I'm asked for. So the final thing that I want you guys to do for this, for Tuesday, September 1st, is I want you to try a problem on your own. So I will check this in class. That says Monday. It should not say Monday, so let me change that. I'm going to check this in class on Tuesday, September 1st. So you're buying bottles of a sports drink for a softball team. Each bottle costs $1.19. What function rule models the total cost of the purchase? And then I want you to evaluate the function for 15 bottles. Should be pretty simple. Follow the example that we just did, and then I will check it in class on Tuesday, not on Monday. So have a good rest of your weekend, guys. See you next week.